Record, and here we go. Okay, so guess we've integrated already moment of inertia of a rod. We've integrated moment of inertia of a hoop before, but we've never done a disc, and so we're going to do it. It's just the process as integrating the moment of inertia of a rod. It's just slightly different. So we're going to say the disk has a total mass, capital M, and a outer radius, capital R, and then yeah, and the moment of inertia equation that we got is the integral of r squared dm, right? And remember that means remember that means that by saying r squared, integral of r squared dm, what we're saying here is we know the moment of inertia of a point mass. It's the mass times r, the distance away from the axis of rotation, squared. In this case, with the disk, it's a disk rotating around its center of mass, right? And so what this equation is saying is add up all of the little masses, so dm1, dm2, dm3, we got a bunch of little chunks, how far away they are from the axis of rotation, square it, and just sum all of that up. If I had a computer, I could just make a formula out of this. It'd be a pretty simple formula. It just means add up all of the little dm's, square the disk and their distances squared, and then I would let the computer do it for a while, and after a period of time, I would get an approximate equation that would do a pretty good job. But people aren't like computers. Well, sometimes they are, sometimes they're not. So we figure out other ways to get around having to do an infinite sum of something. And that's kind of what this process is how do I get around having to add up that infinite sum? So it's a uniform disk. That means it's got the same density. Here's an example of a uniform disk, right, that we've done before, and it's a uniform disk rotating about its center of mass. As we did last time, we're going to use density to solve this. We did the same thing with the rod. Again, I kind of want to emphasize that. We did the same thing with a rod. So I'm going to go over some of the densities that we went over before. One of them is volumetric density. We did that with the planet and things like that, right? So we generally use rho for volumetric density, and that's the total mass over the total volume. Rho, that's the Greek symbol there, is what we tend to use for volumetric density. We've also seen for the moment of inertia of a rod, we use lambda. That tends to be the notation that College Board uses, is lambda. When I learned linear density, I used mu, whatever. So they don't have to always be. So, and that's the amount of mass per unit length. Well, that's volumetric density. This is linear density. You can probably guess there must be a density for area, right? And there is. It's the amount of mass per area, per unit area. I know, right? And the symbol we tend to use, again, you don't always have to use this. We tend to use sigma. Sigma is like a little, I don't know, like an O with like a curl after it. It's a little, yeah. Yeah. And that's baby sigma, not capital sigma. Capital sigma is the E. Okay. Oh, yeah. And again, so I'll quickly say, yeah, this is mass, volume, mass, area, mass, length. Questions so far? Okay. And please feel free to ask questions. Don't just think because we got a video here. Oh, I don't know. No, please do. Okay. So all of these, right? We could also have the what we call the itty bitty teeny bits, right? We could say because the density is the same if it's uniform density, it'd be the same little bit of mass over a little bit of volume. That's the whole idea, right? If you have a lot of it or a little bit of it, the density is the same. So that's a little bit of mass dm over a little bit of volume dv. You could do sigma dm over dA, or you could do lambda dm over dl. So again, we're using density to solve our problems for us. You'll see why in a moment. So again, this is little bit of mass. This is a little bit of volume. This is a little bit of, I'll just keep copying and pasting this. Little bit of mass. A little bit of mass. This is little bit of area. And this is a little bit of length. In fact, some of you had this equation on your equation sheet quiz, right? dm over dl. Yeah, all right. Some of you did, some of you didn't. What we're going to use is this one, the area one. And so I'll show you why in a second. But questions for me here so far? We're okay. Okay. All right. All right. So here's the big idea. You can imagine the disk, right? And so what we do, instead of doing all those little bits of mass, remember, the goal is often trying to, because R is a variable here, and so the goal is often to replace dm with something in terms of R so that we can then integrate. And the technique here is, essentially you can imagine if I got a potato peeler and I started to peel off strips of the disk, right? Peel off strips of the disk. So it's not a disk, but I got a tape piece of a roll of tape here. It's essentially like I'm doing this. Go all the way around, rip off a piece, and then I've got a little bit, a little chunk here. So, and then the little chunk, so you can imagine like I ripped off a piece here or here, and then it's going to have a bit of thickness dr, right? So with the tape, that bit of thickness is the part you can barely see here. So for the video, there you go, that little bit of thickness right there. The part you can barely see. That's the thickness dr, because that's what was around the tape before. So here's now the thickness dr of that little strip that I've pulled. Now, here's the thing. I'm going to cheat a little bit because I can't really, when I go to put this up here, I can't really draw that thick. It's so small, it's like a hair fracture small, a hairline small, right? So I'm going to cheat and say this is dr, right? Instead of saying this, I'm going to say this is dr. So instead of this, I'm going to say this is dr, just so we can, you with me? Yes? So what we do is, again, it was around the tape. It was around the tape. I'm going to rip it off like I did. And then I take that and I put it up there, right? So it's a strip around here. I pull it off. And now I've added it up there. So this is the thickness dr. And again, I'm going to make a bunch of little strips of dr. What about its height? In terms of r, I should say. So I pulled it off 2 pi r, right? Because I pulled it off of the circle of the disk, right? And I could take this one and add it here, but I'll do that. I'll do that later. So yes, this is going to be the circumference, basically, 2 pi r, because that was the little bit of tape that I just ripped off. You with me so far? Yes? Yes? Yeah. Okay. So this, then, the area of this tape is dA, the little bit of area. And any area is the base times the height. I'm going to say height times base, right? And so dA is going to be this little bit of height, 2 pi r, times the little bit of base, dr. So again, down here, this little strip that I've made, so the area of anything is the base, or I'll say height times base, and so dA, using all of this data, is going to be 2 pi r times dr. Questions so far? So again, I'm using this equation, which says sigma equals, and again, that's the area density, which is uniform in this case, dm over dA. I'm going to multiply both sides by dA. I'll get sigma dA equals dm. And sorry. So, and then I could take all of this, because this is dA, and I can plug it in to there. So this becomes then there you go. So this becomes then sigma, instead of dA, we're going to write 2 pi r dr equals dm. And now going back up to this original thing right here, I'm going to take all of this and plug it in there. Because that was the whole point. So now I basically have the moment of inertia in terms of r's, or constants. So this can be rewritten as the moment of inertia is the integral of r squared, and then in here is sigma times 2 pi r dr, and that's it. That was the hard part. Questions so far? You guys are never this quiet. It's because we're recording? You don't want your voice? No, okay. There you go. All right, thank you. Thank you. There you go. Okay. So, well, I can simplify this a little bit because I got r squared times r. What's that going to be? R cubed. So we're going to say the moment of inertia is the integral of r cubed dr, because all these other things, sigma, constant. That's the density. It's a uniform density. 2 pi, constant. We can pull those out, and this is now a much easier integral. So I'll say 2 pi times sigma, and then the integral of r cubed dr. The only thing I need left is to find the limits of integration. Typically, I would make your origin the center of mass if you're trying to find like the center of mass of a disk. So I usually make the origin here at the center of mass, or I'll make an X. Make it make it there, and then you're integrating from 0 to capital R, right? Because basically what I'm doing is adding up each little strip. It's like an onion layer, right? I'm adding each little onion layer up until I reach big R. So what does that look like then? Well, here we go. So I'm going from 0 to R, and now I do the integration. This should be old hat to you. What's the integral of r cubed? 1/4 r to the 4th. So we got r to the 4th over 4, and I'm going to evaluate all that from 0 to r. If I plug in 0, that's just going to give me 0. So plugging in big R, capital R, I get the moment of inertia is 2 pi times sigma times capital R to the 4th over 4. Oh, I can see this 2 cancels with this 4. I'll have 2 here. And that gets me 1/2. Oh, got the 1/2. So far, so good. But now the only thing, I got to get rid of the pi and the sigma. And the sigma is where I'm going to, what can I replace sigma with?
M over M.
Yes, the total mass over the total area, right? We did the same thing with when we did the rod. So we got 1/2 pi. Instead of sigma, it's the total mass over the total area, but it's a disk. What's the area of a disk? Pi r squared. And in this case, it's going to be the total area, so that's pi capital R squared times r to the 4th. And we can see, lo and behold, pi cancels, r squared cancels. So 2 r's cancel up there, and we get the moment of inertia of a uniform disk, the one you know and love, 1/2 mr squared. Woo! I know, yeah. So yeah, there you go. Questions before I summarize everything we just did? So the process here, it's exactly like the rod. It's just instead of using little chunks dr and replacing it with lambda, in this case we're using little strips of area dA and replacing them with the circumference and dr. It's always the same, yeah, shtick. So you want to choose a convenient origin, almost always the center of mass. Replace dm with dr using some form of density expression. In this case, we replaced the area. We replaced it with the area density equation. With the rod, you replace it with a linear density equation. Establish limits of integrations. In this case, we went from 0 to r to capital R. Integrate, and then simplify and replace density term if necessary. Questions for me here? Nah. Okay, so um, I bring this up because I will say you will have to integrate the moment of inertia of something. Majority of the time, 90% of the time, I don't know how, mostly it's a rod, right? Which we've been doing since the beginning of the semester. But every once in a while, it is a disc. And in fact, last year, they got the disc.
Oh.
So look at that. Look at me go. This up here is, hey, thanks. This up here is a non-uniform disk, so it's got some linear density. But here's a problem that you can try using the same methods that I did. See if you can get it. I'll pull this up as you guys are working on other things throughout. Okay. Bye. Bye.